Welcome to the Evolution of Radiant Mixing presented by Taco. I'm John Barba, and in this program we will discuss the various methods available to you to mix water temperature for radiant systems using mixing valves. Taco has several options ranging from a simple three-way thermostatic tempering valve to motorized 2, 3, or 4-way set point valves, both of which will maintain a fixed water temperature for the radiant system. We also offer a motorized mixing valve with an integral outdoor reset control. In Part 1, we'll discuss the need to mix based on the types of boilers used on a job, and we'll discuss some options. So let's get started. So why do we need to mix water temperatures for radiant systems? Well, it's obvious. Radiant systems require lower water temperatures than a typical hydronic system would. Baseboard, for example, needs 180-degree water under design conditions. A radiant system, however, may need only 90-degree water for a basement slab or 130-degree water for a joist heating system with aluminum heat transfer plates. When using a high-temperature cast iron boiler for these systems, some sort of a mixing device will be needed. Cast iron boilers typically operate at a high limit of 180 degrees and require boiler return temperatures of 135 to 140 degrees to prevent flue gas condensation. When applying radiant to a cast iron boiler, a mixing device will be needed, as well as some sort of protective piping arrangement for the boiler. Often in modern hydronics, you'll encounter multi-temp, multi-load systems. These hybrid systems will have several different types of heat emitters, baseboard, radiators, hydro-air, and several different types of radiant floor installations all on the same job. These multi-temp, multi-load systems will require different water temperatures and different mixing devices. In addition, many radiant systems may have 2 or 3 different water temperatures for different installation methods. For example, there might be radiant in the basement slab that needs 100-degree water, while there may be joist heating in the upper floors that needs 140-degree water. When using a cast iron boiler, each installation method will need its own mixed temperature. You may also run into a situation where zone-by-zone mixing might be beneficial. For instance, let's say you were installing a joist heating radiant system on the first floor of a home, and part of that first floor is carpeted while the rest is hardwood. The carpeted areas may need 150-degree water, while the hardwood areas may need only 125-degree water. These areas will most likely be zoned separately and could benefit from separate mixed water temperatures. Low-temperature modulating condensing boilers, also known as mod-cons, are increasing in popularity in the U.S., especially with radiant systems. These boilers are designed to run at lower water temperatures than cast iron boilers. In fact, the lower the water temperature, the better. The more efficient these boilers will be. In theory, with low return water temperatures, a mod-con could easily reach the mid-90% range in terms of efficiency. In a single temperature radiant system, a mod-con would not require any additional mixing. For example, let's say you're using a mod-con for a joist heating job that requires 135-degree water. Simply set the operating control on the boiler for 135 degrees and then pipe the system directly to the boiler as per the manufacturer's instructions. No additional mixing device would be needed. However, what if you have a basement slab that needs only 95-degree water included in that same system? Well, the boiler is making 135-degree water, handling the high temp demand, while a separate mixing device would be needed for the lower temperature radiant slab. In addition, zone-by-zone mixing may also be beneficial with a mod-con boiler, especially when mixed floor coverings create wildly different supply water temperatures for a radiant system. When using valves to mix for radiant heating systems, there are 3 basic options. The first is the three-way tempering valve. It's a simple, non-electric thermostatic valve designed to maintain a fixed supply water temperature on the radiant side. Next is an electronic motorized version of the tempering valve called the iValve Reset. This valve provides much more precise water temperature control than does a tempering valve, as well as providing boiler protection. And finally, there's the motorized reset iValve. This valve includes a fully functional outdoor reset control built right into the control head. The reset valve provides not only outdoor reset control, but also boiler protection and a warm weather shutdown function. We'll discuss all 3 of these valves in detail. Of the 3 mixing options, the most basic option is the three-way tempering valve. What you're looking at here is the Taco 5000 series tempering valve. The tempering valve provides a fixed water temperature to the radiant system. If the dial on the valve is set for, say, 130 degrees, then the valve will supply a steady 130 degrees all winter long. It's a very simple mixing device. It's non-electric, so no additional wiring is needed, and it has very few moving parts. The Taco 5000 is, relatively speaking, a low initial cost mixing option. However, since the tempering valve provides a fixed supply water temperature all winter long, comfort in the living space will be determined by the zoning package. When using a fixed temperature control strategy, plan on zoning aggressively to prevent rooms that are either too warm or too cool. Also, when using a cast iron boiler, it will be important to protect the boiler from low return water temperatures and possible flue gas condensation. This can be done with either a boiler bypass loop, as you'll see shortly, or with a primary-secondary piping arrangement, as you will see in a subsequent segment. Here's a typical boiler piping arrangement for a cast iron boiler with a tempering valve using a boiler bypass loop. Note the bypass between the boiler supply and the return. This bypass is used to protect the boiler from low return water temperatures when the system is in operation. We'll discuss this in greater detail momentarily, but first let's take a look at the actual operation of the three-way valve. The three-way valve has three ports: a hot port, a cold port, and a mix port. The hot port is connected to the supply line from the boiler, the mix port is piped to the radiant system itself, and the cold port is piped to a bypass from the radiant return. The valve's job is to mix the radiant return water with the boiler supply water to deliver the desired radiant system supply water temperature. Inside the tempering valve is a bimetal thermostatic gland that shrinks and grows based on the water temperature it senses. As the gland shrinks and grows, it will open and close a shuttle valve on the hot or the boiler supply port. Let's say we want 130 degree water in the radiant heating system. The green dial on the valve is adjusted to a setting for 130 degree water. When the system is filled with cold water, the bimetal gland will be in the shrunken or the retracted position, and the shuttle valve on the hot port will be wide open. As the system heats up, warmer boiler water will be circulated through the radiant system, and as the water temperature continues to rise, the bimetal gland will expand. And as the gland expands, it will gradually push the shuttle valve on the hot port closed. Once the temperature reaches the desired 130 degree level, the gland will be in the fully expanded position, and the shuttle valve on the hot port will be completely closed. At this point, the radiant portion of the system will be hydraulically isolated from the boiler portion of the system. That means as long as the shuttle valve is closed, water will only flow through the radiant system whenever there's a call for heat. It will not go back to the boiler. However, as the water flowing through the system cools, it will lose temperature. That means cooler and cooler water will be hitting the bimetal gland, causing it to shrink. As the gland shrinks, the shuttle valve on the hot port will open, allowing more hot water from the boiler into the radiant loop, and thereby increasing the radiant supply water temperature back to the desired 130 degree level. However, once the shuttle valve does open, a portion of the cool radiant return water, which could be as low as 115 degrees, will be sent back to the boiler. The boiler bypass circuit is critical to protecting the boiler in this application, and here's how it works. The boiler circulator, you'll note down at the bottom, remains wired to the boiler high limit control, and it will fire whenever the boiler fires. On the supply side, a portion of the hot boiler water will head to the three-way tempering valve, while the rest will flow through the bypass and head back to the boiler. Meanwhile, when the tempering valve is open to warm the radiant system water, cooler radiant return water, in this example 115 degrees, is being sent back to the boiler. Where the end of the bypass and the radiant return piping meet is a mix point. The hot boiler water will mix with the cooler radiant return water at that point and temper the water going back into the boiler to a level above the 135 to 140 degree mark most of the time. There will be instances of condensation with this piping arrangement, but the idea is to minimize the amount of condensation. The key to making this work is the bypass valve. This valve should be a globe valve. It works best here because they are designed for linear throttling. A ball valve is designed to be either fully opened or fully closed and aren't really considered balancing valves. Globe valves aren't all that expensive either. Most plumbers know them as stop and waste valves. To set the bypass valve, use the following steps. At system startup, set the valve to the half-open position. Then fire the system and watch the water temperature on the outlet side of the three-way valve as it increases. If the water temperature does not reach the desired level, the globe valve is probably too open and should be closed incrementally until the desired water temperature is reached. Once that happens, remove the handle. Finally, a quick word about circulator location. In most hydronic applications, it is preferable to place the circulator on the supply side of the system, pumping away from the expansion tank. This will provide for better air control in the system and promote optimum system performance. In the example you're looking at, however, you'll note that the circulator is on the return side of a packaged boiler. In this example, the boiler circulator has but one job, and that is to keep the flow moving through the bypass to increase the return water temperature back to the boiler above the condensing point. Well, that's it for part 1 of the evolution of radiant mixing. Thanks for joining us, and please make sure to join us for part 2, where we will be taking a closer look at the three-way tempering valve and go over a system sizing problem.